All right, welcome. What we're going to start off with is we're going to start with a differential volume of a fluid, and from there we're going to be trying to find the basic equation of statics and how it's going to help us with our problem at hand. So let's say that we have some fluid, some liquid with a. Let me draw it better. Some fluid slash liquid, and the thickness of it is dz. All right. And A is going to be our cross-sectional area measuring from the top down. And our liquid is it's actually in a much bigger volume of liquid. This is just one piece out of the entire whole. All right. And we're going to make this point right here our Z. And if we go from Z across some thickness of dz, very, very small, the top up here is going to be Z plus dz. And now what you'll see is that we have one microscopic volume of the liquid immersed in another volume of liquid. And what we're going to try to figure out is what are the forces acting on our individual liquid. So when we go to it, we're going to get that we have a force pushing up from, let me draw this again. So let's say we have a fluid in a jar, and we're looking at this individual point right there. And this point right here is going to be our entire system, if you will. And at this point, at this individual dot, we're going to have a force up from, so let's start off by saying that force can be measured by our pressure multiplied by the cross-sectional area. So force equals pressure times our cross-sectional area A. So at this point right here, we're going to have, let's call it point C. All right, at point C, we're going to have a pressure point, a force pushing up with a force of pressure times our cross-sectional area, and a force pushing down from the water above it or the fluid above it. Then that is going to be the pressure times the cross-sectional area. Now the pressure right here at Z is going to be different than the pressure up here at PZ plus DZ, which is the thickness of our membrane. And what we're going to learn is that our DZ axis actually goes up as we move across our membrane. So as we move further up, we're going to get bigger numbers for our z-axis. So what we're going to do next is we're going to actually we're going to balance our forces, all right? So we know that force equals mass times acceleration. Force equals ma. And in this case, we're going to assume that there is no acceleration because there is no change in velocity. Our velocity for this system right here, there is nothing moving in or out, and we have a velocity constant of 0. So our acceleration, since there is no change in velocity, is therefore going to equal 0. So that means force is going to be equal to 0. And now when we have to calculate all our forces, we have all our forces are going to equal 0. And that means we're going to have a force of PZ plus DZ times the cross-sectional area. And that is going to be negative. And we're going to have a force of our mass times the acceleration of gravity, so minus mg, and that's just of that individual particle in the volume of fluid. And then we're going to have plus a force of our pressure at the initial z on the bottom here times our cross-sectional area. And that is going to be all equal to z. So what we can able to do next is we can actually move values around and try to figure out what our pz and dz are going to equal and how we're going to use our cross-sectional area. So what we're going to do first is we're going to take out like terms. We're going to have our cross-sectional area is going to be multiplied by pz minus pz plus dz equals mg. And now there's just one problem here, and our problem is that we know that our mass times acceleration of gravity, that our acceleration of gravity is going to be negative. So what we need to do is we need to divide over a negative so that we get A times cross-sectional area of pz plus dz minus pz equals our negative mass times acceleration due to gravity. And what we can do next is we can actually simplify these variables even more. And what we're going to do is I'm going to carry on, and I'm going to show you how we can get this into something that's derivable, and so we can show how, what's our question asking? So we can show the density in terms of the ideal gas. So first we're going to have mass times gravity. Alright, so for this variable liquid that we have, we know that we're going to have a density, and we know that density is equal to mass over volume. So that means mass is going to be equal density over the volume, alright? Alright, since we know that volume equals mass, well, our density equals mass over volume, and then that mass will equal density over volume, we know that the volume is just the amount of area from this point right here to this point right here. So what we can do is we can divide our cross-sectional area from that top to the bottom to give us the volume of how much liquid we're actually working with. So in essence, we get the equation pz plus dz minus pz equals negative mass over the area, and the area is going to be equal to the volume, and then now we just have a negative rho g. But what's perfect about this is that this pz plus dz minus pz is just a change in pressure over a distance of dz. So since it's a change in pressure, we have not triangle. We have delta P, and this can be expressed over dz for the change in pressure from point Z to point Z plus D. So a change in P and a change in our height of our fluid is now equal to a negative rho G. From here, what we can do is we can integrate to begin our solving of the problem so that we can figure out what we're going to actually do with this equation. So let me move the screen again. Get it right there. And what we're saying is that we have a liquid. We're going to express this as P1, and this is P2. What we're trying to find is the difference in pressures as we move down in height. So right here and between right here, we're going to get different pressures and different heights that equate to help our equation relative to the density multiplied by our negative acceleration of gravity. So what we're going to do first is we're going to find, let's do integrals. So doing the integral, we first need to get a differential on both sides. So we're going to multiply the dz over. So we have the integral of dp expressed from P1 to this P2, and that is going to equal negative rho g dz, although the negative rho g are just constant. So now we have integral of dp is just going to be p evaluated from P2 to P1. And that's going to equal negative rho g it's going to equal z evaluated from z2 to z1. As you see, this will be z1, this will be z2, and it increases as we go up. Yeah, all right. So following that, we get that we have P2, so pressure at 2 minus pressure at 1 is going to be equal to the negative rho g of z2 minus z1. And what we get with that is that our expression is going to tell us, well, it's showing us what our expression is going to tell us. And at a change in pressure equal to rho times gravity, we're going to have an equal and opposite change in position of where our differential fluid is relative to the volume in the container. And what I'm going to show you here is why dp over dz equals negative rho g can really turn out to. Since we want to get this in terms of pressure and volume, what we're going to need to do is we're going to need to take our density and put it in terms that are going to help us. Alright, so now we're going to have dp over dz equals rho negative g. And what we can do with this is that we know that our density is also equal to molecular weight over RT times pressure. And what we can do is we can set that right into our equation. And we'll get dp over dz equals negative molecular weight times the pressure of G over RT. And what we have is we have our initial equation that we set out to look for. So I'm going to next is explain why this works. So what we have is at some variation of pressure, we're going to be equal to molecular weight times gravity over RT to the change in Z, which is Z is going to be our height. So if we have a mountain, all right, we know that this is going to be Z1 equals 0, and that this is Z2. As you go up the mountain, our position is going to increase and our relative height is going to increase. But at the same time, we're also going to have a pressure change from P1 to P2. And we're actually going to have less pressure as you go up. So this is how this can be used. But this is basically the equation, the basic equation of statics. And in the end, we get dP over dz equals the negative pressure times the molecular weight of G over RT. So we're going to have our internal changes equal du, and that is going to be and equal to our any changes in heat exchange, which we're not going to have, minus our force, which is just going to be our pressure of the system. Let's draw our system real quick. So what we have here is we have an air bubble going up, and it's getting bigger as it goes up from Z1 to Z2. And we're going to have a pressure 1 and a pressure 2. And what we're doing here is that we're going from here all the way up to here. But luckily for us, this is an adiabatic reversible process. So that means it's reversible. We can go from position Z1, position 1, to position 2, and we can also go from position 2 back to Z1 with no force required of changing anything. But what this does mean is that there is not going to be any temperature change within, for right now, we're going to say that there's no temperature change acting on the exothermic system at hand. But we do know that the force that we're going to have is going to be our pressure times our specific volume. So from here, we get that all of the internal changes of energy is going to be caused by a temperature change. We know this because at P1, for this pressure, there's no way we can have the same temperature at this pressure and the same temperature at this pressure. So for internal changes, we're going to have our only change is going to be in temperature. So we're going to draw a CV dt. And since this is a adiabatic, there are no outside heat transfers or thermal reactions causing anything to our system. So this is going to be equal to 0 minus, and for pressure, we don't actually know the pressure. We don't know what it's going to be. So, but we do know that PV equals RT. So we're going to put P equal to RT over V and express this in terms of also temperature so that we can be able to find something later, and so we can put this in terms of dV. They're going to match our differential. So what we're going to do next is we're obviously going to try to solve this. So we're going to switch up, mix and match both sides so that we can have a dt over t well, less dV is going to be equal to a negative R over V dV. What we get here is we want to integrate both sides, so we get CV times the natural log of t, evaluate it from T2 to T1, and that's going to be equal to negative R over the integral of dV over V, and that is going to be equal to over V, same thing, so negative R to the natural log of V evaluated from V2 to V1. So what we're going to have is CV natural log T2 over T1, because you'll have a natural log of T2 minus natural log of T1, and when you do natural log minus natural log, you can put them into one natural log and differentiate. And then we're going to have this equal to negative R of natural log of V2 over V1. Except there's going to be a special case here where we realize that we don't want this expression in terms of volume. We are trying to get it in terms of pressure 1 and temperature 1. So we're going to come back here and we're going to see that now that we've derived in respect to volume, we're actually now going to put back into our pressure. So V is going to be equal to RT over P. So we're going to get, first we're going to get, let's do everything to the E so that we have T2 over T1 to the CV equals E, no, not E, equals V2 over V1 to the negative R. All right, from here, what we get to do next is we get to understand our actual system at hand. What we know is that we are doing a adiabatic process, all right? Adiabatic reversible process. And this is of an ideal gas. So what we have assumptions that we can make. The pressure of the surrounding of the system, since since it is an adiabatic reversible, the pressure of inside the system is going to be equal to our pressure outside the system. And so that means that our P's are going to be equal to each other as they move up and down, which is making this process reversible. Also, since there is no heat exchange, there is no heat added or not added or destroyed, I would say, in a way, whenever we go from position 1 to position 2. What is also great about this is that since it's adiabatic reversible process, that we're using the ideal gas. So we're able to use ideal gas equations like PV equals RT for an ideal gas and get rid of the number of moles because it's just one mole for an ideal gas. So what we get to do next is that we also get to understand the relationship between pressure and systolic volume. So what we're going to do is we're going to sub in this RT over P for our V2 and V1. For V1, we're going to get P1. And when you do that, you get RT over P2 over RT over P1 to the negative R. So what we get is we're going to get a T2 over T1 equals P1 over P2 to the R. And we still have this as CV, so we're going to multiply everything by T2 over T1 to the 1 over CV. That is going to give us T2 over T1 equals P1 over P2 of negative R over CV. Oops. Of negative R over CV. And now this is what we've been trying to get to. This is using the ideal gas law, a relationship between pressure and temperature. But we can take this a step forward and actually dive deeper with this to make it look a lot cleaner and clean it up. So what we're going to do is take this, just move it up there, and we are going to rewrite our equation so that we have T2 over T1 equals P1, pressure 1, over pressure 2 times temperature 2 over temperature 1, all to the negative R over CV. If we separate this, we can actually get T2 over T1 of 1 plus negative R over CV is going to equal a P1 over P2 of negative R to CV. What we can do from here is we can multiply the entirety, and we will get T2 over T1 of 1 plus negative R to CV times CV of CV plus R equals P1 over P2, of negative R over CV times the CV over CV plus R. And what we're going to get from this is that T2 over T1 is going to be equal to P1 over P2 and R over CV plus R to the negative. All right. And so what we have here is a way to find the temperature based off our change in pressure. What I love about this is that if we start at pressure 1 and go to pressure 2, we'll have a variable to understand our temperature 2 and temperature 1. What we can also do is that we can have this little air bubble. Let's say it's still at a reversible, but let's say there's that point, and there's even this point, all right? And now what we have is that we have a P1 and a T1, but this is just P1 plus N and T1 plus N, and then we have a P1 plus 2N plus T, and then we have a T1 plus 2N. What I'm saying is that we can also write this as T over T1, so our final temperature is going to be equal to our pressure 1 over our final pressure to negative R over CV plus R. So we're able to relate this equation to any change in a system of adiabatic reversibility for any pressure or temperature, starting from initial to whatever change it likes to do with its instance and height. But what we do know is that, let's go to our equation, let's go to our question. That we're assuming that our temperature remains constant for this individual piece. And in fact, that we know it does not, especially as we change in pressures. So what we need to do is we need to find a way to relate this change in temperature into our ideal gas of adiabatic reciprocity that is going to help incorporate a more exact answer for our change in temperature. So once we found our equation that we're going to use to understand our temperature and pressure, what we need to understand about our system is that we do have a temperature that is varying, and our temperature is not going to remain constant the entire time, especially as we change our height, and our pressure, they're going to be changing. What we need to do is figure out a way to process and evaluate how we're going to see what equation are we going to use to go from temperature 1 to temperature 2. So first we're going to write out our ideal gas equation model we used earlier. dP over dz is going to be equal to the negative pressure times molecular weight times gravity times RT. And what we're going to do with this is we're going to understand that this T right here is the same as this T right here, because it really is just T over T1 equal to P1 over P to the negative R over CV plus R for any temperature and position, for any temperature and pressure at any position we choose to go to, whether up or down. And so since we know that that T is equal to this T, we're going to get that T is equal to T1 times P1 over P of negative R over CV plus R. And what we get to do with this is we get to throw it right into that equation. So how we're going to do that is we're first going to separate everything, and we're going to get dP over P is going to be equal to mg of R, and we're going to have alpha equal negative R over CV plus R, just so we don't have to keep writing that. And then we're going to get that what we're going to do is we're going to have equal to negative R over CV plus R, and we're going to get that dP over dz is going to be equal to negative P of 1 plus alpha mg over R times T1 of negative alpha. And so what we get to do next with this is, did I forget the P1? I forgot the P1. Yep. And I'm going to take this, put it way down here so we can start our question 3. I'll just rewrite the equation. We're going to have dP over dz equal to a negative P of 1 plus alpha times molecular weight of G over R times T1 negative rho times P1. And what we get from here is we actually get to differentiate, and we'll get that negative P plus alpha over dP, integrate, is going to be equal to the integral of mg over R T1 to the negative alpha P1 of dz. So for here we get to differentiate. We're going to go from, we know this is going to give us a negative 1 over alpha of P evaluated from P final to P1. And that's going to be equal to, since all these are constants on the outside, times RT of T1 times P1 to the negative rho of Z F minus Z1. And from here, we're able to take all these and do a PF to the negative alpha minus P1 to the negative alpha equals P1 negative alpha of mg over RT1. And we're also going to have alpha times our entire equation because we brought it over from right here of ZF minus Z1. So next we have our final pressure. It's going to be equal to, we'll add P1, that would be P1 times 1 plus alpha, sorry, due to gravity, of RT1 times ZF minus Z1. 1 plus, that sums that, that sums that, that's in there, that's in there, that's in there. And now we're going to take that negative alpha and distribute it across the entirety so that we're going to have a PF is going to be equal to P1 because we're going to multiply everything by a 1 over alpha. Yeah, negative 1 over alpha. So that's going to be 1 minus alpha mg over RT1 of ZF minus Z1 of 1 over alpha. And that is now going to give me PF equal to P1 1 minus alpha mg RT1 Z plus ZF Z1 to the CV plus R over R. Once we are here, we have an equation that is going to help find our final pressure based off our temperature change and our variable position. All right, and so now that we have everything, we are able to also, just so that no one gets confused here, alpha was always equal to R over CV plus R, and 1 over alpha made that exponent. But from earlier, let us not forget that T2 over, not T2, T final is equal to T1 times P1 over P final to our rho. And so our final temperature is going to be equal to T1 multiplied by P1 over PF of rho. And we're going to substitute this PF in right there. And what's going to come out of that is we're going to get TF is equal to T1. We're going to plug the P1 in there. And when we plug that in there, we'll get all that over P1. So P1s would cancel. 1 minus rho. Rho has an R. So R over R. Our R's would cancel. That would go on the bottom. And since there's a rho times our 1 over rho, that is going to be canceled out, equals 1 over 1, which equals just 1. So then we'll have 1 minus molecular weight times gravity of CD plus R times T1 times our change in height. And now, what we've been able to do is, from the very beginning, is if we have a change in pressure or a change in height, we only need our distance and height and our initial temperature to find our final temperature and final pressure and all things that go such with. Now let's make sure we've answered every question here.